Hello ATS 114 students, Dr. Shragi here, and I'm here to give you some help with Lab 5, the Atmospheric Moisture Lab. I really like talking about atmospheric moisture, and one of my favorite things about it is latent heat. By now, regardless of what section of the class you're in, you've learned all about latent heat. I love that word latent. Latent means hidden, not apparent. If you have a latent desire to kill your roommate, it means that you're not going around telling everybody. It's hidden, it's deep-seated. And in the same way, latent heat is a real type of heat, but it isn't something you can measure with a thermometer or something. It's heat that is hidden in the fact that the water substance is in one of 3 different phases. And it took a certain amount, it consumed a certain amount of heat to change that into a liquid, but you'll get some of that heat back. You'll get all of that heat back, that latent heat back, when you have another phase transition. And your lab manual has a diagram very similar to the one that's up on the screen right now, where it's showing you all the different phase transitions like melting and evaporation and condensation and sublimation and all those kinds of processes. And it shows you that each of these processes involves either absorbing or releasing a certain amount of latent heat. What the diagram, both on the one on the screen and the one that's actually in your lab manual, could do a lot better is to tell you that these are in units of per gram. So like, for example, the process of evaporation is absorbing latent heat at a rate of 600 calories per gram. Evaporating 1 gram of water absorbs 600 calories from the air, from the material and even the environment around it. So for example, when you step out of the shower after having taken a shower, water begins to evaporate off of your skin and you quickly feel cold. The process of evaporating is absorbing a very large amount of heat from the environment, and it's hiding that heat. That heat is not gone. It's hidden in the fact that we have changed liquid water into water vapor. Some point in the future, we'll get that latent heat back. It'll be released when that water vapor condenses back into liquid water. And in this lab activity, there's sort of a pattern that will be helpful to you if you notice. All the processes that move on this diagram from right to left, like condensation, deposition, and freezing, those are all processes that release latent heat into the environment. They take heat that was hidden in the water substance and release it back to the environment. For the purposes of an atmospheric science course, the really important one is condensation. In a cloud, when you have water vapor condensing into liquid water drops in the cloud, every gram of water vapor that you condense into liquid water is going to be releasing 600 calories of latent heat into the cloud. And that's a lot of grams of water vapor in a cloud. So that's a whole lot of heat that is being released into the environment. In the same way, any process on this diagram that goes from left to right, like melting or evaporation or sublimation, all of these processes absorb latent heat. They are absorbing heat from the environment and hiding it in the fact that we've had a transition of the phase of the water. So like, for example, evaporation. It takes heat from the environment to change water vapor from water substance from a liquid to a gas. That heat isn't gone. You'll get it back when you have condensation. All of these phase transitions involve either absorbing or releasing latent heat. Your lab manual uses the word consuming rather than absorbing latent heat. That's kind of a poor choice of words for what is happening. It isn't consuming the heat, it is absorbing it. It is storing it in a way that you'll eventually get back. Consuming seems to kind of imply that you wouldn't be getting it back. Now, obviously, humidity is an incredibly important concept in something like atmospheric sciences, and as a consequence, we have a number of different ways to describe the amount of water vapor that is in the air. And we're going to be focusing on 4 of those ways in this lecture. One of them is to describe water vapor in terms of its vapor pressure. Vapor pressure is just saying, there's a total amount of pressure right now. You can think of pressure like as the weight of the air above you, but perhaps a better way in this case to be thinking about pressure is it's the force of all those little molecules in the air bouncing around and hitting the surfaces and so on. And when you define vapor pressure, what you're saying is, of all that pressure that is, all nitrogen molecules and oxygen molecules and carbon dioxide molecules and so on, how much of that pressure is due to the water vapor molecules bouncing against the surface? So it has units of millibars, and just for your information, the units of vapor pressure are, typical values of vapor pressure are about 0 for completely dry air to about 40 millibars for really, really moist air. Vapor pressure is a measure of how much water vapor there is in the air. We could describe right now in the air with you, in the room with you, maybe there's 12 millibars of vapor pressure. In contrast, we have a second number called the saturation vapor pressure. The saturation vapor pressure is not a measure of how much water vapor there is in the air. It's a measure of how much water vapor there would be in the air if the air were saturated. Okay, we're not going to take the time right now to explain saturation and how what's the whole deal with why there's a limit to how much water vapor the air can hold and so on. That's what your lectures are for. That's what the book is for, and so on. But you know that there's a limit at any given temperature to how much water vapor the air is going to be able to hold. And in fact, your lab manual provides you both with graphs and tables of that information, where they're showing on that curve of that graph there how much water vapor the air would be able to hold at any given temperature. That is a graph of the saturation vapor pressure. We're not saying the air is holding that much water vapor. We're saying that is the most water vapor the air could hold at that temperature. Your instructor in the lab may have actually even, or in the lectures may have actually used the right word for that. That's a graph of the Clausius-Clapeyron equation. I know that that term is actually in your book. Anyway, so if I say that term again, you know what I'm talking about. This is a graph of an equation called the Clausius-Clapeyron equation. Another way to describe this, actually quite related to vapor pressure, is mixing ratio. Mixing ratio is an idea that comes to us from chemistry, actually. You can kind of think of it as a recipe. It's saying to make the current air that you've got right there in your sample, what did it take? It took this many grams of water vapor added to this many kilograms of dry air. Okay, so it has units of grams per kilogram, grams of water vapor per kilogram of dry air. And strangely, it actually has about the same range as vapor pressure does. It ranges from about 0 grams per kilogram for very dry air to up to about 40 grams per kilogram for dry air, for moist air rather. And just like we said before, for vapor pressure, mixing ratio is an actual measure of how much water vapor is in the air. That's in contrast to the very related saturation mixing ratio, which is not saying that's how much water vapor there is in the air, that's saying how much water vapor there could be in the air at this given temperature. How much water vapor would the air be holding if it were currently saturated? And actually on page 50 in your lab manual, they provide you with a table and with a graph of what the saturation mixing ratio is for a range of temperatures. It's actually another form of the Clausius-Clapeyron equation. We've just kind of done some conversions to work with different units and so on. So we have this idea of vapor pressure and its corresponding saturation vapor pressure. Saturation vapor pressure not being how much water vapor there is in the air, how much there could be. And then we have this analogous idea of mixing ratio and saturation mixing ratio. I don't know why the manual doesn't just stick with one or the other. It seems like it would simplify the problems a little bit, but whatever. They want to make sure that you understand both of these ideas. Also, we want to understand how both of these ideas are related to relative humidity. When you turn on the weather channel, please don't be turning on the weather channel. There's garbage. Watch something better for your weather information. But when you watch the weather channel, they give you the relative humidity as your measure of humidity. Relative humidity, though, is a terrible measure of humidity. It isn't really a measure of humidity at all. It's actually a measure of how close the air is to being saturated. So, for example, there's two ways we've seen so far already that would work for defining relative humidity. You could say it's the vapor pressure divided by the saturation vapor pressure, or you could say it's the mixing ratio divided by the saturation mixing ratio. Either way, it's a way of saying how close am I to being saturated, which is neat, but isn't really what we wanted. We wished that relative humidity was a measure of how much moisture was in the air, but because that saturation vapor pressure or saturation mixing ratio depends on temperature, relative humidity actually depends on both the amount of moisture in the air and the temperature. And that's kind of awkward. Let me give you a little example that I like to use in the lectures. Here's a little house in the winter, okay? And let's say that we went outside of the house on that winter day and we measured the temperature and the vapor pressure. Alright, I measured the temperature and it was 0 degrees, and I can use my graph of the Clausius-Clapeyron equation or those tables, and I can find out that the saturation vapor pressure, which I'm abbreviating here, SVP, is 6 millibars. Then let's say with some piece of equipment we measured that the vapor pressure is 5 millibars. Okay, then in that case, outside of the house on that day, the relative humidity is 5 divided by 6, which works out to 83%. Okay, now, suppose we open the door and some of the water vapor, some of the air from outside comes in to your house. Well, inside of your little gingerbread house here, in the winter, you're not going to have the temperature in your house be 0 degrees. You're going to use your furnace to heat it up. So let's say we've heated up that air and it has now a temperature of 20 degrees Celsius. That's like 68 Fahrenheit. That seems reasonable in the winter. We use our graph of the Clausius-Clapeyron equation to determine that the saturation vapor pressure, the amount of water vapor the air could be holding at the present time, is 24 millibars. All right, well, we haven't done anything to add or remove any water vapor from the air, so the vapor pressure is still 5 millibars if we measured it. Which means that the relative humidity now is 5 divided by 24, which works out to 21%. Well, that's a little awkward. We changed the relative humidity without changing the amount of water vapor in the air at all. We just changed the temperature. That's not really what we want. Not to mention, just kind of thinking about the situation here, a relative humidity of 21% is not very comfortable. Your lungs are going to be drying rapidly as you breathe this very dry air into them. You're going to need something like a humidifier to keep the air more comfortable in your house. In the same way, we can kind of draw a similar example in the summer. Here's my little house in the summer. Let's say I was going to go outside of the house and I measured that the air temperature around the house was outside the house was 30 degrees. What was that? I don't know, 86 or something like that. And the saturation, 86 Fahrenheit. And the saturation vapor pressure, if I pulled that up from the table or from the graph of the Clausius-Clapeyron equation, is the saturation vapor pressure is 44 millibars. All right, and while I was out there, I measured that the vapor pressure was 23 millibars. All right, so my relative humidity is vapor pressure divided by saturation vapor pressure, or works out to 23 divided by 44 is 53%. Okay. Now we open up the door and we bring some of this hot air from outside into the house. So we are not going to leave leave the air at this temperature of 30 Celsius. We're going to cool it with our air conditioning. If we cool the air down to a temperature of 20 degrees Celsius, again, our Clausius-Clapeyron equation will tell us that the saturation vapor pressure, the amount of water vapor the air could be holding, is now 24 millibars. But we haven't done anything to change the amount of water vapor in the air. We haven't had any condensation or any evaporation or anything. So, I mean, if we measure the vapor pressure of the house, it's 23 millibars. But that means the relative humidity inside the house is 23 divided by 24, which works out to 96 millibars. Once again, very awkwardly, we just changed the relative humidity by changing the temperature. We didn't change the amount of moisture in the air at all. Not to mention, the relative humidity of 96% is going to be really, really high. That's, the kind of relative humidities at which like mold starts to grow in your house and so on. You're going to need like a dehumidifier to keep that under control. Alright, so we have this idea about relative humidity. It turns out it's actually really hard to measure relative humidity. In the lecture and in the book for the lecture, I know there's some examples of instruments that can measure relative humidity, but the little secret here is it's actually not very accurate and not very easy. It's more accurate to actually calculate the relative humidity if you know two pieces of information: the dry bulb temperature and the wet bulb temperature. Both of those pieces of information come to us from an instrument called the sling psychrometer, which you're going to get a chance to use today. A sling psychrometer is really pretty straightforward. It's just two thermometers mounted on a handle, like what you see in this picture here. One of the thermometers is just a very ordinary thermometer, which we're going to call the dry bulb thermometer. That little part down at the end of the thermometer that holds the mercury or the alcohol spirits or whatever, that is called the bulb. So the dry bulb is the one that doesn't have any water on it yet. The other one is going to have a little cotton sock on the end of it. I've always heard it called a footy, but whatever, like little babies' Japanese have footies. Anyway, it's a little cotton sock on the end of it, and you get it wet. As you swing, that's why that one's called the wet bulb thermometer, because the bulb is wet. And when you swing this thing around and air flows over those two bulbs of the thermometers, the dry bulb temperature is measuring the temperature of the air, and the wet bulb thermometer is colder than that, because water vapor is evaporating off of the little footy, which is a cooling process, and so the wet bulb temperature will be less than the dry bulb temperature. The difference between the wet bulb temperature and the dry bulb temperature is a number called the wet bulb depression, and you use the dry bulb temperature and the wet bulb temperature on pages, I think it's 52 and 53 in your lab manual, to actually determine the relative humidity. The equations to do it are a bit of a mess, but quite accurate. It just provides you with a table. I think in the lab manual they want you to measure the wet bulb and the dry bulb in 4 locations. We'll probably keep it simpler than that, just to keep, because time is short, but your TAs will tell you how to do that. Finally, there's the dew point temperature. This is actually how meteorologists prefer to describe the amount of moisture in the air. The dew point temperature is the temperature to which you would need to cool a sample of air in order for it to become saturated. And to understand why that is, we need to go back to one of these graphs of the Clausius-Clapeyron equation again, and I'm just going to zoom in on part of the graph right here. Now, an aspect of these kind of graphs that can be a little hard to picture. Any given spot on these graphs can be thought of as like, maybe think about this the other way around. Any given air parcel you could come up with maps to a spot on this graph here. So for example, that little dot right there, that dot corresponds to an air parcel with a temperature of 20 Celsius and a mixing ratio of 10 Celsius. And any given temperature and any given mixing ratio maps to a location on that graph someplace. Now, in this particular case, you can see that we are below the curve of the Clausius-Clapeyron equation. If we wanted to know, for example, the saturation mixing ratio on this diagram, we could go up and see that, oh, the saturation mixing ratio is 15 grams per kilogram. Heck, while we're at it, we could compute the relative humidity and see that it is 10 divided by 15 equals 67%. And that's all nifty, but there's actually a better way to describe the moisture in this air. And that is to take that point where that air parcel is on that graph and slide it to the left until it encounters the curve. That's the equivalent of cooling. See how we're going down towards lower temperatures? And when we encounter the graph of the Clausius-Clapeyron equation, we now have an air parcel that is saturated. We have reached a point where the amount of water vapor that is in the air is all the water vapor that that air parcel is able to hold. That's the dew point temperature. Okay, that kind of graph is kind of fun to play with, and there's a couple of questions on that in your lab manual that you'll enjoy getting a chance to mess with. Hopefully this lab activity will be one that you can get done fairly quickly. I think you'll actually be quite a bit better prepared for the second half of the course once you have these moisture variables in hand. All right, please let your TAs know if you have any questions, and I look forward to seeing you next week.